Hello, my name is Mama Najri and I'm gonna describe a bit about data 50 random data that I have for BOD reading, DOC reading, and SFS. As you can see, table 1 is the table which is 50 data from 4 different locations, which is I took it from randomly. The data is before I segregate into location 1, 2, 3, and 4. Okay, table 2 is about BOD, DOC, and SFS reading from location 1. From the table 2, I already segregate, start from the table 2, and then 3, 4. I already segregate into location 1, 2, 3, and 4. So we can see the mean, median, max, minimum, and standard deviation for each data that I collect from different locations. So here at the table 2, the BOD for location 1 is 1.24, DOC 2.07, and SFS 3.49. But the standard deviation for SFS is far, which is if you put it in plus minus 2, it's not within the range, it's very far from the mean, which is the result is 12.45 for the standard deviation SFS. Meanwhile, for the BOD and DOC, within the range plus minus 2, which is nearer to the mean. For table 3 is also BOD, DOC, and SSF reading from locations, but this is from the location 2. Here I can say there are 4 data that I collect from location 2, but the BOD, DOC, and SFS from the location 2 have the same results, which is the mean is 1.43, the DOC is 2.13, and then the SFS is 3.39. What I mean they have the same result is from location 2 we have 4 data, so the 4 data have the same value of POD, DOC, and SFS. That bring us the standard deviation for POD for the location number 2, 0, DOC 0, and SFS 0. Table number 4, POD, DOC, and SFS reading from location number 3. From the location number 3, I have 10 data from the location number 3. So the mean for the BOD is 1.54, the DOC is 1.89, and the SFS is 3.15. Bring us the standard deviations from the 10 data is 10 for SFS, which is very far from the mean, and this is not good data to interpret. But the OC and BOD is the standard deviations for BOD is 0.08 and the DOC is 0.26. Within the the standard deviation is near to the means, so I can use this data to interpret the results. Okay, table number 6 is the mean table for BOD, DOC, and SFS reading from 4 location water resource. Here I already make it summarized, which is you can see here from location number 1 I have 14 data, location number 2 I have 4 data, location number 3 10 data, location number 4 22 data. When I sum it all, I get 15 data, and the mean for BOD, DOC, and SFS each location I stated on the tables. Same also for the standard deviation for BOD, DOC, and SFS for each location I stated on the table, but you can look here on the BOD and DOC if the result for the standard deviation is near to the means. Meanwhile, for the SFS is very far from the mean. So for the next action I take to make an explanation in graphically, I will not include SFS, because the SFS, the standard deviation is only location 2 is 0, but the rest is far from the mean. So I only use BOD and DOC for graphically explanations. Okay, now the graphically data part, which is I use bar charts for the graphically data. Then this is the bar chart of the mean variation for BOD and DOC readings from 4 location water resource, which I collect 50 random data. So this is the graphically data. So from the graph, from the bar charts, I can conclude that The highest BOD reading is at the location number 3, with the lowest DOC reading is also at the location number 3. The BOD readings for 4 locations is between 1 mg per liter and 1.55 mg per liter, while the DOC readings for 4 locations is between 1.8 mg per liter and 2.15 mg per liter. As you can see at the graph, at the bar chart here, the highest DOC reading is at location number 2. Well, that's it for the explanation for my bar charts. The next slide is a test at 5% significant level to look if there is a difference on DOC readings between 4 location water sources. This is the DOC readings. Okay, as you can see, the DOC readings between location of water resource already tabulates in the DOC readings for location 1, 2, 3, and 4. The next, I will do the Anova table, which is I started from the models, the assumptions, the restrictions, and the hypothesis. Which is, the hypothesis is hash nulls mu1 equal to mu2 equal to mu3 equal to mu4 versus hash1's mu1 is not equal to mu_j for at least one ij. After the hypothesis step is the test statistics, which is the calculation for to get the SST, SSSTRT, SSE, MSTRT, MSE. This test statistic is to complete the Anova tables. After the calculation, you can see that my complete Anova tables is summary and the Anova. The decision rules that I have here is I put it, the critical value is f 0.05 3, 46 is 2.8. So the decision rules is we will reject hash nulls if the calculated f value is larger than 2.87. Reject hash null if f test is more than f 0.05, 3, 0.46, which is the f criticals. But the table that you look, which is the Anova result that I get, is the f test is less than f criticals. So the conclusion here I can say we fail to reject hash null at level of significance 0.05, which is 5%, since the calculated f is 1.83 is smaller than the critical value of 2.8. So this means there are no statistically significant difference in mean variation for DOC readings between the 4 locations of water resource. So that is the conclusion for the Anova. There is no statistically significant difference for the mean.
Hi there, my name is Raimis Lan, and I will explain about the linear regression model related to the BOD and SFF. And in this slide, you can see that there is a 50 random data being collected, where we have a BOD data and also SFS, and I get the average for the both data, which we get for the BOD, we get the 1.3948, and while for the SFS 3 to 7.5. As we all know, the linear regression equation that we're going to use is the y hat equal a hat plus beta x, and which give us the value is for the alpha we get the 352.54, while for the beta, we will get the minus 17.95 for x, and we get the R2 equal to 0.0626. So here in the chart you can see the linear regression or the linear relationship between the BOD and SFS as shown in the slide. Test linearity between BOD and SFS given the 1% significant level. The hypothesis for this is the hash null will accept if the p-value of f significant is less than or equal to 0.01, and hash 1 will accept if the p-value of f significant is not less than or equal to 0.01. So here we get the p-value of f significant is 0.0626. Therefore, we fail to reject the hash null as there is an linear relationship between BOD and SFS, and the result is the result for the p-value is the more than 0.01. Therefore, R squared equal to 0.0626, and the correlation for the R is the square root of the 0.0626, where we get the 0.2500. Therefore, the values of the R close to 0, and there is no linear relationship between the x and y. BOD readings are assumed to have a normal distribution with mean 1.5 and variance 0.135. And here I built a table where we have the BOD data, expected count, which is the mean for all the 50 data, and we have a x2 value where the BOD will minus with the expected count, and then we squared it and divide by the expected count. So the hypothesis for this is the hash null, where we'll accept if the BOD readings are assumed to have a normal distribution with mean 1.5 and variance 0.135, and we will accept or we will reject the hash null if the hash 1 where the BOD readings are not to have a normal distribution with mean 1.5 and the variance 0.135. Therefore, we will reject the hash null if the p-value is less than x squared. So by using the goodness of fit text, I build the data, I get the total for the data, for the expected count, and for the x2 squared, and where we get the total for the data is 33.78, while for the expected count we get the 34.87, and for the x squared we have the 0.458. So with the mean is the 1.4, with the chi-squared is the 0.458, with the p-value is the 1. Therefore, the conclusion for this is we reject the hash null as the BOD readings are not to have a normal distribution with mean 1.5 and variance 0.135. So that's all the presentation for our group, and thank you very much.